No, but that's no laughing. The answer is how does Sarah Lake happen?
What's that?
How many times she was playing in this not scary?
It was my first vlog. So of course it was gonna be a bit quick. Yeah, I have to
Wait, no.
morning. So they don't need me. I'll take it like last example.
Hello. I wanted to, actually, I'm going to tell you guys at the beginning of class about this because I decided with my other block that we are going to have a quiz on section 1.1 because we're going to finish it today. We're going to have a quiz on Tuesday, okay? And the homework is going to be pages 14 to 17 and 26 to 28. And those will help review for the quiz. All right. So basically, it's going to be about calculating reaction rates from data, from a table, from a graph, and we're going to finish going over that today. And also, it's going to be about determining what method you could use to measure a rate. We've talked about some of those already, like the volume, measuring the volume of a gas or the pressure of a gas or the pH. We're going to finish going over that today as well. So we're finishing it all today, and we're going to go over stuff. Yes, Isaiah? It is not including unit 0, other than the fact that you need to understand ionic equations enough to know that you cannot use a spectator ion to measure the rate of a reaction. Does that make sense?
Yeah.
Yeah. So unit 0 is not going to get quizzed or tested or anything, but you being familiar with ionic equations will help you in that you'll be like, oh, I know that when I have HNO3, I actually really have H plus and NO3 minus. So if I needed to monitor pH, I could do so, right? So it's not directly being quizzed, but you know, your understanding of that material will help you. Okay? Alrighty, so let's go. I will put this back up again later. It's also going to go up on Teams, so don't worry. But for now, we are going to go to page, what page is it? Oh, this is the wrong one. There we go. Page 11. And today we're going to be specifically learning how to show our work when we calculate rates so that you won't lose any part marks, okay? So I'm just going to simplify this. We've got reaction rate is equal to the amount of chemical species used or produced over the change in time. So we could simplify that by saying the rate is equal to a change in amount over the change in time, okay? And if we're measuring amount of a substance, we could be measuring grams, or we could be measuring moles, or we could be measuring molarity, or we could be measuring liters. Okay, there's all kinds of different things that you could use there for the amount. And time could be minutes, it could be seconds, it could be any sort of thing. Minutes, seconds, hours, any of those are good, okay? And we're going to start by looking at the example on this page. But I'm going to close that door first. You know I'd be in the hallway. Okay, so we have a question here, and it has a lot of numbers in it. So what I would like you to do is I would like you to take a look at all of these numbers And once we have looked at these numbers, let's decide which of those numbers do you need to use in order to solve part A. And then once you've figured that out, we will solve part A together so you know exactly what to show in your work to get full credit. So you guys figure out which of those numbers are useful. I'll take attendance and then we'll solve it together. Okay. G1, are you here? You're right there. Perfect. Hannah. Hannah here? Not here. Okay, that's what I thought. Okay. Pi is here. Aaron's here. Brooklyn is here. Laura is here. Cher is right there. Thank you. Sarah's here. Grace is here. No, Grace is here. And Sean is here. I got my last names mixed up. Okay. Ethan's here. Jenya's here. Jonathan's here. Jody is right there. Perfect. Kylie's here. Dorsey's here. Daniel is away. Daniel's away. Minnie's here. Samira's here. Juwan's here. Isaiah. Michelle. Jessica is right there. Excellent. Justin. And I haven't written Ellie on this list yet. Ellie. Okay. All right, to solve that question, what are we going to need to use? Will we need to use our 2.45 grams of zinc to find the volume of H2 produced? No. Okay, maybe we'll use it in the next part B, but not for part A. We don't need it. Will we need to use the 115.3 milliliters to solve for volume of H2 produced per second? No, because it's the volume of HCl, which was not what we're looking at. Will we use our 1 molar? No. 15 degrees? No. 2 minutes? Yes. Okay. Yay. Going to use that one. And how about the 494.6 milliliters? Yes, because that time we're talking about the hydrogen gas. Do we need to use the 1.01 grams of zinc? Nope, not for part 1. So one of the things you have to do with problems is sort out which information is useful, because there's often more than you need. So how to show our work for part A? We are going to start by writing what we are finding. What are we finding? We are finding the rate. Okay, so you want to write rate. And then you write equals. And then you're going to show how you will calculate it. Okay, and we can say it is the change in this case, what is the change in? The volume of H2 gas over the change in time. Now, you don't want to just be like, okay, plug your numbers into your calculator and spit it out the other end. You now want to take the numbers that are given to you in the question. So we have 494.6 milliliters, and our time is 2.00 minutes. Now, just before we get too excited about this, you can just show your work this way. Technically, change in volume should be the final volume minus the initial volume. But in this case, what is our initial volume? 0, okay? So if the initial volume is 0, you can leave it out. Okay, and technically same thing with our change in time. It would be the final minus the initial, but again, If Ti equals 0, we can leave it out. And we can just say, okay, it's just 494.6 milliliters over 2 minutes. And the only thing that we need to do here is, what is the question actually asking us for? If we just divide this, am I going to get my final answer? No, because it says it wants it per second. So you could either do like this and just convert your minutes into seconds. So our minutes will cancel out, 1 minute for every 60 seconds. Four 4.6 divided by 2 equals, divided by 60 equals 4.1216 repeater. Please tell your partner, what do I need to do with that answer to make it good? Sig figs. Okay, so let's do that first. How many sig figs should we have? 3, because remember the 1 minute and the 60 seconds are exact, so we don't worry about them. So it's the 2.00 minutes that limits us. So 4.12 units. What are we left with in terms of units? Milliliters per second. So we have milliliters per second. And if you're a very, very kind student, what will you do? Box it. And I might actually put milliliters of H2 per second, just so it's clear exactly what I'm talking about. Okay. Now, what do you need for full credit? You need to show this, show the formula. You need to show units in work. You need to have correct sig figs. Whoa, jumping about. And then you need to have units in your answer. Okay, and whenever you look at my answer key, you will find, hopefully, if I've done it correctly, all of those things. All right? Now, technically, you could, if you wanted to, do one of these steps in your head because it is super easy. You could have, if you wanted to, put 494.6 milliliters, and instead of dividing it by 2 minutes, you could just divide it by 120 seconds, because you can say, I know that 2 minutes is 120 seconds. And that just saves you a step, but it doesn't matter. Okay? All right. Let's do our second one. We want moles of zinc used per minute. What is our relevant information for this one? Well, we got some information about zinc here and some information about zinc there. So we know that our initial mass of the zinc is 2.45 grams. And we know that our final mass of the zinc is 1.01 grams. You wouldn't have to write this step. Okay, that's not required. If you can keep that in your head, that's all right. And we still know that our time is equal to, change in time is equal to 2 minutes. Delta doesn't look much like a delta. There we go. Okay. What should you start by writing to solve? We want moles of zinc per minute. There's actually a few ways to attack this problem. But one good way is to start by showing the formula. So let's start it that way. We'll look at another way to do it in just a moment. Okay, so we have rate is equal to, And technically we want moles of zinc per minute, but we can do our conversion later and we can say, I'm going to find our rate in mass of zinc over time. Delta mass zinc over delta time. And remember, when we have a change, we're going to do our final minus our initial. So we have 1.01 grams minus 2.45 grams. Yes, we're going to end up with a negative number, but that shouldn't be too surprising, because what are we doing with the zinc? Are we making zinc, or are we using it up? We're using it up, so that's why it is a negative number, okay? And the change in time is 2 minutes. So we have 1.01 minus 2.45 divided by 2 equals 0.72 grams per minute. And if we wanted to, we can continue on this same line. We could say, I don't want grams per minute, I want moles per minute. So I need to cancel my grams and find moles. And what do we use to convert between grams and moles? Molar mass. Where do we find that? Periodic table. All right, and I think that is what, 65.4? Yeah, 65.4. Oops, I forgot my negative sign. Hang on a second. 1.01 minus 2.45 equals 1.44. Oh, never mind. Oh, daft girl. Sorry, I did the division by. Never mind, I'm having issues in my head. Now, how many sig figs should we actually have here? We should have 3, because even though this is a 0.072, that's just what my calculator spat out, we still have, if we were to look at this, this is 1.44, that has 3 sig figs, yes? So we should still have 3 sig figs in our final answer. So we'll go, we have 1, 2, 3, so that's going to be 0.0110. And then the only units we have left are moles of zinc per minute. And it should be negative. And it should be negative. Now, I'm going to tell you guys right now, I'm not going to get too excited about whether you call it negative or whether you call it positive, because if we write negative, that means it's getting used up. That's great. But if the question says, what is the rate of consumption of zinc per minute, then technically you wouldn't say my rate of consumption of zinc is negative 0.0110. Like, that's weird, right? So we would use a positive value there. But I feel like that is a really sort of nuanced distinction that's hard for students at your level. If you feel comfortable with that kind of thing, you can attempt for the correct usage of positive or negative, but I'm not going to worry about it. If you have a positive on there, I'll be happy. If you have a negative on there, I'll be happy. If you're like me and you drop your negative sign, this is the one instance where I'm not going to get worried about it. Okay? So let's not worry too much about positive and negative. I will leave that for your university's professors to worry about. Yes? Okay, cool. You could have, if you wanted to, you could find your change in mass of zinc first, 1.01 grams minus 2.45 grams equals 1.44 grams. And then you could say your moles of zinc, you could calculate that. And then you could take your moles of zinc and divide by your minutes. Yes, and then you could, so there's different ways of doing this problem. Does that make sense? It doesn't have to be always written in the way I've written it, as long as you've shown all your units and they all cancel properly and you've shown all your steps. Is good? Okay. Next, we're going to look at some data from a table, because one of the things you need to be able to do is calculate from a table what the rate is. So could you please start by writing the balanced formula equation for the reaction of zinc with hydrochloric acid? And if you don't happen to know what hydrochloric acid is, although it is really our most common acid, so you should know, there is actually a table of common acids in your pink booklet. It is on page 6. So if you want to check that out, you can take a look there and you can skim through the list and see if you can find hydrochloric acid. All right. So if you're ever needing to know the formula for an acid, they are there for you if you need them. But hopefully HCl is just a really easy one. It's like the iconic of all acids, hydrochloric. Yeah. What is the charge for zinc? Take a look on your table of common ions. So that would be page 3. Okay, and you're going to say, oh, it's a positive ion, so I look under zinc, and it is +2. Okay? People always ask, do I need to memorize the charges? And the answer is no, but zinc is a really common one, so if you happen to stick it in your brain, it is handy, right? You can always look it up, but it's kind of nice to just know it. Pardon me? It's a metal, so the only metal that is not solid is mercury. So zinc is a solid, yes. Now, hopefully you remembered that zinc is a positive ion, so which ion does it kick out? Does it kick out the H or the Cl? Kicks out the H. And hopefully you remembered that hydrogen is one of the diatomic elements, and over on the right, it's on its own, so it is H2. And do we know the state of hydrogen? It's gas. Do we know the state of acids? Acids are always aqueous, because if they're not in solution, they don't behave like acids. They behave like little molecular substances. Okay, so if they're gaseous or whatever, they just don't behave like acids. So they're going to be aqueous. And if the HCl is aqueous, what does that mean about our zinc chloride? It will also be aqueous because it's all in water and it is soluble. Do we need any coefficients? Yes. We're going to put a 2 there. Without drawing out a complete ionic equation, could you guys determine, can you see if there are any spectator ions in that reaction?
Yeah, same hydrogen. Oh, I'm sorry.
Now remember, when things are in compounds, they have charges, right? You wouldn't write these, but you can just kind of, put them in small for yourself so that you remember. Has zinc changed? Yes, it's changed from 0 to 2+. Has hydrogen changed?
Yeah.
It's changed from H+ to neutral. How about chloride? Chloride was negative, chloride is still negative, so it has not changed. So if I were asking you, what could you use to monitor the rate of this reaction? Could you use mass of zinc?
Yeah.
Yes. Could you use concentration of hydrogen ion? Yes. Could you use concentration of chloride ion? No, because it's a spectator ion and it doesn't change. Could you measure volume of gas? Yes. Could you measure pressure of gas? Yes. Could you measure mass of the system? Yes. And by system, I mean the whole thing. Why can we measure mass of system? The reactants are, sorry? The mass of the reactants is equal to the mass of the products. So why is it, though, that the mass of the entire system will change over time here? And what conditions do we need in order to measure the change of mass? We need to have an open system. And what's an open system going to do for us? It's going to allow the gas to escape. What will happen to the mass of the system over time? It's going to decrease as that gas leaves. Okay? Alrighty. So we're dropping our zinc into 1 liter of 1 molar HCl. Let's remind ourselves that that capital M there is pronounced molar. And what does M actually stand for? Molarity, which is the moles per liter. Okay, that's just a little reminder of what that means. We're given all this data and we're asked to find the average rate of reaction. And when we are asked to find the average, we're going to use the final and initial values. Data points. So if you're asked to find the average, you'll use the final and initial data points. What if I said, though, find the average rate between 4 seconds and 16 seconds? What would you use? The 4-second data point and the 16-second data point. But if you're just asked for the average, you're going to use the final and initial. So here we have the initial mass of zinc. And here we have the final mass of zinc. Here we have the initial time, and here we have the final time. So it's not much different from the last questions we did. It's just you need to be able to pick which data points from the table to use. Yeah? And once again, we need to write the formula. So we're going to start by writing rate. Then we're going to write equals. And then what are we going to write? Change in the mass of zinc over the time, change in time. Then we're going to take our final value, 0.006. Now, if you don't want to write grams here, you could do like this. You could say 0.006 minus 0.016. You could put these in brackets and write the grams at the end if you want to. You could also just write 0.006 grams minus 0.016 grams. Either way is fine. And then we have 20 seconds. Final time minus the 0 seconds is the initial time. Now, before we get too excited about doing anything, when we calculate 0.006 minus 0.016, what do you recall about significant figures when we are doing a subtraction? That's the rule for multiplying and dividing. When we're multiplying and dividing, we use the smallest number of sig figs. What's the rule for adding and subtracting? Yeah. Yes, you use the smallest number of decimal places. Okay, so for adding and subtracting, when we're adding or subtracting, the number of sig figs in the answer depends on the smallest number of decimal places. Okay, so that's a little tricky because we don't use that rule as often. So it is important to remember. So if we take 0.006 and we subtract 0.016, my calculator says negative 0.01, which looks like 1 sig fig, yeah? And if I looked and I was like, if I tried to do my smallest number of sig figs, I'd be like, oh, 0.006, 1 sig fig. However, I know that I should go to the smallest number of decimal places. How many decimal places do we have in each of those numbers? 3. So this should actually be 0.010. Okay. Another way to think about it is that when you're adding or subtracting, you round to your first uncertain digit. The uncertain position is the thousandths position. So I've underlined our uncertain digit in each case. So that is in the thousandths position. So this here has 2 sig figs. And then in the bottom number, we have 20 point seconds. It's grams. So we do our division. And we get negative 5 times 10 to the negative 4. Sig figs. How many? 2, which means what do I need to do with my 5? Add a 0. Okay, so I'm going to have 5.0. That gives me 2 sig figs. And then I need to have units, grams of zinc per second. And I would probably, to be kind, box my final answer. So that's part A. Part B asks us to take that grams per second and change it into moles per minute. Now, my question to you is, this is very much like what we did last day. Do you want to take the time to do this today? How do we feel? Anyone want to do it today? Thumbs up if you want to do it. Thumbs down if you don't want to do it. Thumbs in the middle if you don't care. Okay, I've got lots of thumbs in the middle. and I've got a couple of thumbs up, so we're gonna do it, okay? You guys can try it independently because you should be able to do it now. Okay, so we're gonna start with this thing, so I'm gonna rewrite it down here. Negative 5.0 grams of zinc per minute, and we want to convert it into moles of zinc per second. So see if you can do that using the tools that we practiced yesterday. Oh, no, not moles of zinc per second, moles of zinc per minute. And did we have grams? Oh, we started with grams of zinc per second. And I forgot my times 10 to the negative 4. I'm making a huge mess of this, aren't I? Times 10 to the negative 4 grams of zinc per second, and we want to convert it to moles of zinc per minute. That looks better. Okay. Whew.
I do have that sort of story with you. And then yeah. Yes. Yeah. Because I assume that you're going to follow this. And I'm like, oh. No, that's okay, because this is how much I would make my whole second. We're figuring it out per unit, so there will be more, right? So you can just use it. So you use this, and then that. Yeah. How's it going? Good?
R.I.
Yeah. Yes, sure. I'm really sorry I can do it.
Oh.
Yeah. 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 So. Yeah. Oh, that's okay. Good, yeah, that looks good. You're missing our 10, but.
What do you mean? Look at this guy. Just stay warm.
I know. Good. So like from teacher to teacher, they don't change.
Did you get 4.6 times 10 to the negative 4
Yes, I know.
moles of zinc per minute?
Got there.
And I forgot my negative sign, so yes, you should have a negative, but like I said, I'm not going to get too excited whether you have the negative or not, okay? And I'll let you know that honestly, when I was in high school, I always dropped my negatives. Like, I didn't mean to, they just went away. Whoops. My grade 11 algebra teacher actually did not take off marks when I forgot to write my negatives on my final exam, because he's like, you know what you're doing, you just can't remember to write the negatives. And I'm tired of taking marks off. And I'm like, oh, God bless you, that's lovely, thank you. Because I had lost marks, like little half mark here, half mark there, all year long for losing my negative sign. All right, next. We're going to skip this page because it's all about complete ionic and net ionic equations, and we actually did like a whole thing on that, so we don't need to. And actually, we're going to skip to 1.1c. Are we? Hang on. Oh, yeah, we are. 1.1c. Yeah. So we are now on page 18. We have actually talked about most of this already, so we're going to be able to go through it quite quickly. So for example, we might, if we want to measure a rate of reaction, look at the concentration of something. Yes? What's one thing that's easy to measure the concentration of? One substance? Acids. Okay, so if we have hydrogen ion, it's really easy to measure its pH because we have a pH meter, okay? One thing we haven't talked about yet is if we have something that is colored, yes? So if we have an ion which is blue and it gets used up and becomes colorless, then there is actually a little machine called a spectrophotometer. You don't need to remember that name, okay? But there is a machine that will measure the concentration of something that has a color, okay? Colored chemical species absorb light. I'm going to go grab a colorful chemical species. Look at it.
Yes, that's exactly what. We just
Now, this is not a perfect example because the bottles are different, they're different thicknesses, but these are both copper 2 chloride. Can you see how this one is like a lighter color? That's because it's less concentrated, okay? Now, what happens is when light shines on this, it actually absorbs orange light, which means that the blue light is reflected back to our eyes. Okay, so we actually see the blue because this thing absorbs the opposite color on the color wheel. It absorbs orange, so it looks blue. Do you need to understand this for chemistry 12? No. However, if you're taking university chemistry, you will. Okay? So it's nice to know that something appears blue because it absorbs the opposite colors. All right? And the more concentrated the substance, the more of that color of light it's going to absorb. All right? So let's just pop really quickly to page 20. Is it 26? I think. Yeah.
If it looks blue, does that mean it's actually always orange?
It's actually orange, yeah, but it looks blue.
Yeah.
Well, it depends on how you want to say it actually is, because it actually is blue. Do you know what I mean? Because it looks, I don't know. It's one of those, it's a metaphysical question that is beyond my ken. Yes? All right, so we are on page 22. Page 22. So we use this thing called a spectrophotometer or a colorimeter. And this is how it works. We take a visible light source and we shine it, through a little slit. Okay, so we get a really small beam of light, and then we pass it through a filter or a diffraction grating, which works like a prism. Do you guys know what happens in a prism? Like, not just scatters, but if you put white light through a prism, what do you get? You get a rainbow. Okay, so we would have like red and orange and yellow, and I don't have all the colors, and then we would have green, and then blue, and then purple. Okay, I'm sorry I don't have so many colors, but we get the general idea. Yes? Okay, that's my rainbow there. So we get the rainbow, and we actually like tilt this thing up and down, and we select one wavelength of light to actually pass through the sample. I think there's one more slit here that makes it so the particular wavelength of light goes through the sample. Our colored solution absorbs the light. And then what we do is we take a series of solutions of known concentration. So I could take this one and I could say this one is 0.1 molar copper ions. And I could measure its absorbance and I could plot how much it absorbs versus what its actual concentration is in moles per liter. Okay? So let's say for this particular colored substance, if we have a concentration, oh, and then we're using copper 2 ions, look at that, copper 2. If we have a concentration of copper 2 plus of 0.01 moles per liter, what's the other way of writing moles per liter? Molar, okay. If we have 0.01 molar, our absorbance is maybe 0.24 or something like that, okay? We look across here and we say, there's my absorbance. If my concentration is 0.02 for the copper, my absorbance is going to be twice that much, yeah? And we have a lovely little machine, that spectrophotometer will actually give us a digital readout telling us that the absorbance is like 0.48, right? And we do that with a whole series of things. We link something that's 0.03 molar, and we measure its absorbance, and we get ourselves a little graph. And what that will allow us to do is once we have that graph, let's say I have an unknown sample and I put it into my spectrophotometer, and it gives me an absorbance reading of 0.6. If I get an absorbance reading of 0.6, I can read across on my graph and figure out that the concentration is about 0.025. Yeah? Now, you're not going to have to be able to do this year because we have one spectrophotometer for the whole school. Between the whole thing warming up and making all the dilutions and blah, 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 it takes probably about an hour and a half to run one set of students through the lab. So I have 56 students. Even if we were to work in, say, groups of 5, that's still 11 times 1.5. We would have to do it outside of school time. And I'm really, really not willing to spend, 18 hours running one lab because I don't think it's worth it. I think you can, if anyone is actually really interested in trying this out, there is a lovely simulation I can send you to. So if you've got extra time, if you're interested, I will put that up on Teams. You can go check it out if you are interested. Okay, but we're not going to physically do it. In fact, you don't need to know how to do any of this. All you need to know is that you can measure the concentration of a colored substance. And there's a really easy way of doing it. Okay, there's a machine that will do it for you. You don't need to know the name of the machine. You just need to know that if you have a reaction that looks like this, crystal violet, purple, plus bleach, goes to some colorless product. I don't even know what it is. Colorless product. And someone says, how could you monitor the rate of this reaction? You could say we could measure the concentration of crystal violet by monitoring its change in color. Yes? And that's all you'd have to say for grade 12. All right? So all those extra details, how the spectrophotometer works, what the name of the spectrophotometer is, the fact that you can plot the absorbance versus the concentration, you don't really need to know any of that. You just need to know that if you have a colored species, you can measure a change in its concentration. Is good? Okay. Cool. So while we are here, I think we might just go to our, oh yeah, here we go. So you can see here we have a pale yellow color and it turns to blood red. So you can say, oh, I could measure the concentration of that thing by looking at its change in color, okay? We can measure a change in conductivity if we have, oh, look, we have an ionic equation here. This is a complete ionic equation, which is one of the reasons why we did this, yeah? This is a complete ionic equation between potassium iodide and lead nitrate. Whoops, there's no 2 there. You might be given an equation like the one that I have written in red up here. And you might be asked, could I use a conductivity meter to measure the rate of this reaction? And the answer would be yes. But you would have to recognize that, oh, I remember that my aqueous ionic substances are actually split apart. So I actually have positives and negatives, yes? My aqueous ionic thing, I've got 2+ and negative here. So I've got ions, I've got ions. My solid stays together, so it doesn't have a charge. Even though the ions within it do have a charge, they're not charges floating around in solution. And the K has a charge and the NO3 has a charge. What conducts electricity in solution? Like if we have a copper wire, the thing that conducts electricity is the mobile electrons. But a solution, like I could stick a conductivity meter in here and it would say, oh, it conducts. It's not the movement of electrons though. We do have a movement of charged particles though. Electricity is just the movement of charged particles. What charged particles do we have? We have lots and lots of free floating ions, and free floating ions conduct electricity in solution. The more ions you have, the better it conducts. How many ions do we have on the left-hand side of the equation in the reactants? 2, 4, 5, 6, 7. How many do we have in the products? 2, 4. Okay, because we got a 2 in front of the K plus and a 2 in front of the NO3 minus. Yeah, so I got 2, 4. So I got 7 ions, and one of them is a 2 plus ion, so it actually counts for 2. We've got more charges on the left. The basic idea, you don't have to be able to count them specifically. You just need to say there's more ions in the reactants and there's less ions in the products. So what will happen to our conductivity as the reaction proceeds? It's going to decrease, yeah? Yeah. So it's going to decrease as the reaction proceeds. And you could do calculations with that to find the concentration. Again, is that an easy thing to measure with a conductivity meter? Stick the probe in. Yeah, it's not bad. Okay, so you are good if you have a change in concentration of all the amount of ions. You're good if you have hydrogen ion. You can use a pH meter. You're good if you have a colored species. Now, what if you just have some random ion, chloride ion? Oh, what could we measure about the chloride ion? Is there a little probe that we can put in that measures chloride ion concentration? And the answer is no. So we're going to go back even further now. Colored species, those are good. pH meter, that's good. Oh, if I have some ion that I don't have a way of measuring, I might be able to find its concentration via a titration. And this is on page 20. How many people did a titration in grade 11? About half of you. Okay, so those of you who have not yet done a titration, no worries. We're going to do one within the next couple of weeks. It's a good review of stoichiometry. It's a good review of neutralization reaction, okay? The problem is I can use titration to calculate the concentration of something, but here's how it works. Here's my reaction mixture. It is reacting away. Now let's say after 5 minutes, I take a sample. Anyone recognize this piece of equipment with which I am taking the sample? That is a pipette. Fortunately, it's also labeled over there, okay? And I transfer it into what kind of flask? An Erlenmeyer flask. Okay, it's also known as a conical flask because it is kind of cone-shaped. Okay, an Erlenmeyer flask. So now I've got my sample in here. Now, question. We have a reaction mixture. Does it stop reacting because I've taken a sample of it and moved it to a different container? No. So what that means is if you want your data to be accurate, you have to be very, very fast. Okay? I did labs like this in university. It is very, very stressful. Yes? Because you're like, oh my God, I gotta put it in here. And now I gotta taste it. Those of you who did a titration last year, how fast was it to do the whole procedure? Super fast or quite slow? Yeah, it took like half the block for, okay. Now, I can do a speed titration in about 3 minutes. Okay, but I've been doing titrations for 35 years. Yes? Now, if you work for some company, often they have automatic titrators. Oh, those are wonderful, but you won't have those. So if I was to say to you, you have a choice, you've got a reaction where one of your reactants is HCl, and you get to choose, do I want to monitor the concentration of the H+, or do I want to monitor the concentration of the Cl-? Which one would you choose? You would choose the H+ because you stick a probe in and you measure its concentration because it just gives a digital readout for you. Yes? You're not really responsible for knowing how to do a titration at this point, so don't worry if you're like, you went blah, 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 Ms. Spence, I have no idea what's happening. Basically, it means you do a bunch of chemically things. It takes a while and you can figure out a concentration. All right? Let's go back to here. So this is page 18. So measuring a colored species is good. This is easy. Measuring pH is good. It's relatively easy. Measuring concentration of ions with a conductivity meter, relatively easy. Doing a titration is a pain. Okay? So I would not choose it. I mention it because you should know that that technique exists, but chances are you won't ever have to answer a question about it on a test. Okay, we'll have different titration questions later in the year, but not about measuring rates. Okay? Now, we already talked about measuring changes in pressure, changes in volume, changes in the mass of the system when we have a gas. Yeah? So you need to have a change in the number of moles of gas from reactant to product. If you don't have that, if there is no gas present, you cannot use these techniques. Yes? You can measure the mass of a particular solid. I take my zinc, I put it in my hydrochloric acid. I've measured the mass of the zinc before. I throw it in there. It reacts. I get some tweezers. I take it out. I rinse it off to stop the reaction. I dry it off. I weigh its mass again. Can I find the average reaction rate that way? Grams of zinc at the beginning, grams of zinc at the end. Yes? Yes. Could I find an instantaneous rate that way? Could I find a short-term rate that way? Would that be great or not so great? Not so great. Okay, because I would have to dry, take it out, rinse it off, dry it, put it back in, take it out, rinse it out, dry it, put it back in. Like, it's a pain. So this is good for averages only. And we have 2 minutes and I'm going to use them because I want to get through this last little bit here. I'm just going to cross out change in temperature because the calculations are icky. Tough calculations. Okay? We're going to take a look at this one though, because I did promise you we were going to look at what we do with a graph. Ooh, let's look at this little graph here. This is on page 19, page 19. This is probably going to depend on how much physics you've taken. Where is the rate, or maybe math, where is the rate of the reaction the greatest? 0 to 100. Okay, so we have our steepest slope. That means that when we have the steepest slope, we have the fastest rate. At the other end, we have the shallowest slope. And what does that tell us about the rate? It's the slowest rate. So that means that this reaction is slowing down as time goes on. Yes? You could use this data to find the average rate. Which data points would you use to find the average rate? Say you didn't have the actual data table. Say you had to read it off the graph. You would use this one and you would use the last one. We won't talk about instantaneous rates today because I don't think you actually need to know them. No, certainly not for your quiz. I will put back the information about the quiz in just a second, but if you're like, I need to go right now, it will all be on Teams, okay? So if you just need to go and catch a bus, feel free to go and do that. And there's the quiz stuff. Hi. Yeah. Oh, less concentrated just means that you have less solute particles per liter. So this one has a smaller number of blue particles in a given volume compared with this one. If I had the same volume here, this would have more blue things in it than this one would. So less concentrated, more concentrated.
Oh, this is less concentrated because it has less.
Yeah, less solute. Less concentrated means less solute. Yeah. See you. Have a great weekend, everyone. Hi, Michelle.
Hi.
What's up?
That's about.
The quiz is on calculating reaction. It's all in section 1.1. So all of this.
Wait, how about today's stuff?
Pardon me?
How about
Today's stuff, yes. So all of 1.1, 1.2, and 1.1A, 1.1B, and 1.1C. Yes. So pages 26 to 28 is going to practice for those kind of questions. Yeah?
Like.
Yeah?
This is for the English.
Don't worry about this. Just, yeah?
Thank you.